Welcome to Step Response Circuits, the end of Chapter 7. These circuits are just like the source-free circuits we did with RC and RL, but instead of having, when the switch is open or closed, having zero voltage or current through it, we're actually going to have some voltage and current always through it. So our capacitors and inductors are always acting like they're always under the DC circuit conditions, but we have to solve them for different times. You'll understand once you get through it, but just going back, just kind of reiterate. So this is our basic RC circuit from last time, from my first video. The circuit becomes open when time is greater than 0. So that means when time is greater than 0, this becomes a source-free circuit on this side, and we just have to solve for REQ. But up here, when this wire is open or closed, there's always something acting on it to make it a DC circuit. All right, we'll go through this problem, and hopefully that will make sense once we get through it. So here is a circuit for when the time is less than 0, and we are currently trying to solve for the voltage across here. Okay. So as you can see, there is literally nothing flowing through these two resistors because one, this is shorted by a wire, so all this current is just flowing through here in this loop and just ignoring this 4 ohm resistor. And since there's an open circuit right here, there's no current flowing through here because it can't go anywhere once it gets through there. All right, so our voltage when time is less than 0, or our V of 0, is going to be equal to, just from our positive terminal, go down, we go through the 12 volts, plus this is going to be 0 volts. We're going to come up here, and that's it. So it's just going to be 12 volts. And we'll use that in this equation up here, and that'll give us our our voltage of the capacitor. All right, so now we're going to move on to when our time is greater than 0. So with that, this wire, or this switch, will become open, and it'll be an open circuit through here. So that means there's no current flowing through there. So that means there's actually going to be current flowing around this loop, which we can easily find that the voltage across here is just going to be 8 volts. Okay, and just like last time, we're trying to find the voltage across here. And just like in the when t is less than 0, there is no current flowing through this half of the loop because it's an open circuit. So now we want to find V of infinity, which just means the voltage when time is greater than 0. So that's going to be equal to, so I have our positive terminal of the thing we're trying to solve for. So we're going to go through the 12 volts again. So we have 12. Go through this resistor. There's no current flowing through it, so that means there's no voltage across it. And then we're going to come up here across this resistor. We're going to go through the negative terminal. So that's going to mean we're going to have a minus sign. And then the voltage, which is 8. So this is going to be equal to 4 volts. All right. And now finally, we want to find REQ when time is greater than 0. Finally, we want to find REQ when time is greater than 0, just like in our source-free circuits. But now we turn off our sources. So the current source becomes an open circuit, and our voltage source becomes just a straight wire. And we're trying to find REQ with respect to the capacitor. So it's pretty easy to see that REQ is just going to be equal to 7 ohms. And now we basically have everything we need in order to solve the equation. So just to reiterate the equation, it is simply Vc of t. This will be the voltage across the capacitor with respect to time. It's going to be V infinity, or when time is greater than 0, plus V of 0, so when time is less than 0, minus V infinity times e to the negative t over RC. So we found that V infinity is just equal to 4 volts. So it's going to be 4 plus 4 minus, our V of 0, which we solved over here, was 12 volts. So it'd be 12 minus our V infinity, which is 4 times e to the negative t over Req, which we know is 7, times the capacitance, which we know is 2 farads. So Vc of t is simply going to be 4 plus 8 e to the negative t over 14. And that's it. That's our first problem done. And it's pretty simple. We'll just add a new step that we have to kind of realize what's happening when we turn the switch on and off. All right, so here's a step response circuit with, we're trying to find the current flowing through the inductor. So to do that, we still need to find the same thing, just like with our capacitor. We need to find when the voltage or the current flowing through the capacitor when time is less than 0 and when the time is greater than 0 going to infinity. All right, so when the time is less than 0, important thing about the circuit is that when the time is greater than 0 or when time is equal to 0, the switch closes. So that means when time is greater than 0, we have a wire flowing through. So here's our circuit when time is less than 0. And simply, since the switch is open, the open circuit part doesn't really matter. So I just got rid of it in the middle. Okay, so to find IL of 0 is simply just going to be Ohm's law. So we easily see that these two are in series. That's going to be 5 ohms over our 10 volts. And that's going to be equal to our 2 amps. So now that we have that, we're going to move on to when time is greater than 0, which makes the circuit a little bit more complicated. I elected to use source transformation. There's probably an easier way to do this, but just to kind of get rid of this sort of messiness of just current or voltage sources, I just want to make them all into current sources. So boom, boom, boom. All right. So this is going to be our 3 ohms, our 6 ohms, and our 2 ohms. And we're trying to find, and that current is just going to be equal to 10 divided by 2, which is going to be 5 amps. And then 24 divided by 6 is going to be 4 amps. All right. And we're still trying to find the current going this way, or IL. This is going to be our IL infinity. So to do that, we can just combine these 2 current sources and then these 2 resistors. So that's going to be 9 amps going up in parallel with this resistor, and this resistor are 3 ohms. And that resistor is, let me flip my page, it's going to be equal to 1.5 ohms. Okay. Ow. So we can easily do current division to find IL going this way. So IL of infinity is going to be 1.5 over 4.5 times 9. And that is just going to be equal to, this could go down to 1, this is 2. 2 times 1.5 is 3 amps. And now that we have our I of 0 and our I of infinity. All we need left is to find Req. All right, here's our circuit to find Req when time is greater than 0. So I just turned off all the voltage sources, and yeah. All right, so now we need to find the Req with respect to the inductor. So Req, as you can see, is going to be equal to these two resistors in series, so a 2 and a 6 ohm resistor in parallel, I mean, plus this 3 ohm resistor in series. And that is all equal to, are equal to 4.5. 4.5 ohms. So with that, we can compute our final equation, which is going to be IL of t is going to be I of infinity plus I0 minus I of infinity times e to the negative r over lt. So I of infinity, which we found was 3, plus I of 0, which we found over here was 2 amps, minus I infinity, which was 3 amps, times e to the negative Req, which was 4.5 ohms, over our inductance, which is 2 henries, over 2 times t. So our final IL of t is going to be equal to 3 minus e to the negative 2.25 t. All right, and that is step response